Hello grade 12s. I had a question from 4.4 and this was number 7 on page 179, and this one had to deal with a game of bridge is being played, so you need to deal out 13 cards to one of the players, and we've got a few different situations that we're going to try to find the probability for each of these. So for this one, we have to first kind of take a look at what kind of situation we're dealing with. Okay, so 4.3 introduced a binomial distribution, 4.4 was a hypergeometric distribution, and both of these are for determining the probability of something occurring, and that event needs to be either like a success or a failure. Okay, so in flipping a coin and looking for how many heads are flipped, that's something you can either get ahead or not get ahead. Okay, so that would be a success and failure type situation. These two, the questions are going to look similar, but there's one glaring difference. Binomial, this is for independent events. Okay, so just a reminder, independent events mean that whatever happened on the first trial or the first coin flip doesn't affect the following coin flip. Hypergeometric, these are for dependent events, and we know from earlier on that this means that whatever you do the first time is going to affect the next trial. So this question here, we're trying to find the probability of getting all 4 aces when we are dealt 13 cards here. So each time a card is dealt, the probability of getting an ace is going to change. So that means we're dealing with a hypergeometric distribution here. All right, I had to edit my video there. This should have been an A and not an N. Okay, so the A stands for how many possible successful things are there to grab from. So there are 4 total aces in a deck of cards. So the probability of getting 4 aces, well, we're going to have, there's 4 aces. We're finding the probability of getting all 4. How many non-aces are there? There's going to be 48. Because there's 52 total cards, we're going to take those 4 out. And here, out of our 13 cards, 4 of them are already decided. So that's going to leave 9 cards left. So our total here, how many cards are there? There's 52 cards. And we're going to have 13 cards drawn for our game of bridge. So I'd run and get my calculator there, but punching these numbers in, we get 11 out of 4,165, which is approximately 0.00264 or 0.264%. So pretty unlikely to get all 4 aces in these 13 cards. For B, we're trying to find how many of these bridge hands have at least 1 king. So whenever we saw this earlier in the year, we had to be careful because at least 1 king is going to be 1 king, 2 kings, 3 kings, or 4 kings. So we got a lot of different cases there. It's going to be easier to solve this indirectly. So let's do that. So the probability of no kings. So there are 4 total kings. We're saying that we get 0 of them. We're going to multiply that by, there's 48 non-king cards in a deck, so everything but the kings, and all 13 are going to be in that grouping, and we have the same total here as 52, C, 13. So this will be okay, so we've got 6,327 over 20,825. and that's approximately equal to 0.3038, which is approximately 30.38%. Okay, so we're not done here yet. We found the probability of getting no kings. That was 30.38%, but we want to find the probability of having at least one king. So that's going to be our 100% minus our 30.38%. So we're looking at 69 point, what do we got here, 52? So 69.52% chance of having at least one king. All right, in C, we've got two things to account for here. So we've got the probability of 5 clubs and 8 diamonds. So first off, there's 13 clubs. We're going to choose 5 of them. There's 13 diamonds. We're going to choose 8 of them. And this is going to end up looking a little bit different than our formula. But here's what's happening. We have to account for the remaining cards. So in this case, we've got exactly 5 clubs. We've got exactly 8 diamonds. There's no cards left to play. But I'm going to put this in here as a placeholder just to kind of make a point here. So of the remaining 26 cards, so those are your hearts and your spades, we're choosing none of them. Okay, so I'm putting this in here because it helps illustrate what's going on here. We've got 13 plus 13 plus 26, that shows our total of 52. 580 shows our total of 13. That should always be true. Okay, so you can see in the other examples, you add the left side of the C's, they should equal the bottom. The right side of the C's should equal what's at the bottom as well. Okay, so that should always occur. I'm going to grab my calculator here. 13C5 times 13C8 divided by 52 C13. So we've got 2.608 times 10 to the negative 6, so a very, very small chance of this occurring. Or we could have 2.608 times 10 to the negative 4%. Or we could 1, 2, 3, 4. We could have 0.1232608. We can look at it that way as well. Okay? So incredibly unlikely to have exactly 5 clubs and 8 diamonds and no other cards of any other suit. All right, we didn't touch on expected value here at all, but maybe we'll touch on that in another example. Earlier in the chapter, we had a big long formula to find the expected value of each specific thing. In our success and failure calculations, we can shorten it down a little bit with these 2 formulas. All right, have a good day. Talk to you later.